So thank you very much for inviting me to give a few lectures here on hexagons. So that will be the topic of the lectures. And as I will explain, hexagons, at least for now, seem to be a crucial building block for understanding n equals 4 super-Young-Mills, or if you want, the dual string theory. Okay? So they are a building block in the same sense as, say, for an integrable theory. I would say that if you have an integrable theory, the fundamental object is really this S matrix. You scatter two particles and you learn what the S matrix is. It's really the fundamental thing in an integrable theory. For example, you have this nice machine that Shota explained today. You take one particle, you put it in finite volume, it scatters with everyone else, the total phase is 1, and what happens when it meets each of the other guys is acquires the phase given by this S matrix. So really the key object, the fundamental object. It's not the only one. The energy is also important, but the S matrix is better. It's really the S matrix is really the fundamental building block. In the same way, we would say that, of course, in a conformal field theory, the fundamental object are the structure constants, C1, 2, 3. And of course, the dimensions are also good, but the 3-point functions are more important, of course. Just to specify what's the 3-point function, you have to say it's a 3-point function between sigma, sigma, epsilon. Who is sigma? Oh, it's the guy who has dimension, whatever. So the 3-point functions know everything. Right? So this is like the fundamental building block. You take the 3-point functions and you glue together to get your 4-point functions. And as I'm going to explain in these lectures, in n equals 4 super-Young-Mills, / in the dual string theory that corresponds to it, the fundamental object will be these hexagons, and they seem to be really the fundamental building blocks for this theory. And we can speculate whether they could be fundamental building blocks of other things more general, but at least for this particular duality, that seems to be the case. So today I'll mostly draw pictures. So I'll draw various pictures that give kind of an historical or not historical motivation / introduction for why we believe these hexagons should appear in n equals 4 and in more generally in large n gauge theories and string theories. So we'll see in cartoons where these pictures for hexagons come from. So today it's mostly pictures. Tomorrow, the first lecture will be mostly formulae, simple formulae, where we will understand what this hexagon would be when we apply it for a simple theory, say for a free massive boson. And there it will be mostly, it will be very concrete. It will be the extreme opposite of today, where we will hand wave quite a bit. And then in the last lecture, we will try to see how do we go from the free boson, which if you want is the simplest integrable theory where the S matrix is just 1, it's just free, to n equals 4 super-Young-Mills, where the S matrix is more complicated. Shota just computed today the first correction to the S matrix at weak coupling in the gauge theory limit, for example. It's already a richer object. Okay? So that's the plan for today, and I'm hoping to do a little bit of 2 today and a little bit of 3 in the second lecture, because 3 in principle will take more than 1 lecture. Okay, so let's indeed draw some cartoons. And the first cartoon I would like to draw is that of a 3-point function. N equals 4 is a CFT. We said in CFTs the 3-point function are really the fundamental object. So let's draw a 3-point function of local operators in n equals 4. So let's do it. So each operator is a single trace operator, as Shota said. So let's draw an operator, for example, which has 3 fields. So here they are. So this is trace of phi cube. And let's suppose these propagators connect with a guy down here. So there is another operator here that these 2 fields connect with. Let's say this operator has length 4, so there are 2 more here. And these 2 guys connect with an operator here. And this would be here a computation we would do, say, at leading order at weak coupling, where we just weak contract the constituents of each operator. So if I think of each of these operators, this cyclic trace, as we know, we can think of it topologically. This is nothing but thinking that I have 3 closed strings, right? I'm drawing this planar graph. So I have 3 closed strings that I join in this pair of pants way. Right? So this is topologically the same thing. And now, as we see here, so here is the first hexagon. So we look at this triangle inside. It has one edge, 2, 3, 4, 5, 6. So this inside would be our first hexagon. Okay? Now, of course, there is one on the outside of the diagram, which is equally good. So if this inside is one hexagon, this face that I'm painting here, there is one on the outside. I'm just going to draw the beginning of these 3 lines, but you can finish painting. And this would be the outer hexagon. So there would be an hexagon inside, and there would be another hexagon out here. So how would we draw this in the string picture? How would I cut a pair of pants into 2 hexagons? Well, it's exactly how people make pants. They cut along the seams of the pants. So let's draw this to be a dashed line. So you cut, it's really, if you look at your pants after the lecture, you can see that it's exactly like this, that people make pants. You just cut the pair of pants like this. And then the front of this pair of pants is one hexagon, and the back would be the other hexagon. Okay? That goes there. Right? It will cover the back of this pair of pants. Okay? So let's try to see this cartoon emerging from another type of string theory picture, where we look at the worldsheet of the string, and we start describing these 3 strings. So when we have a worldsheet of the string, we think of this as a punctured sphere. So we have the complex plane, and we have 3 strings. So let's say one string comes from this point, right? And if I draw this string growing, it starts coming in, and I start seeing these circles, the string is growing, right? Another string is coming from this point, and I start seeing the string growing. It's coming from the blackboard. And the other one I could draw here, let me draw it at infinity. So the other string is coming from infinity, so there is a big circle. And then this string comes inside, and now it moves in rather than out, right? And this would be what would be the picture. Okay, so this locally close to each puncture, it's exactly the same as what we do in radial quantization. We just draw the lines of constant tau as we move in sigma. But then, as this moves further, we see that what needs to happen, these lines, they need to start bending. They can just not grow forever, eventually drawing something like this. And my strings are coming about. Right? And you see that there were 2 points that got trapped here. So let's mark them in red. So there were 2 points that got trapped. So there is this one and this one. And if you want, there are some special lines, which are the limiting lines of these lines that describe this string, and the outer string, which are some limiting lines where I would connect the operators like this, and like this. Okay, so let's mark these operators a bit better. Right? And there would be this diagram here. Okay? Let me just copy the diagram here, ignoring everything else, so that I don't care about the white lines. I just care about this diagram that I drew, which is this diagram here. Okay? And if you draw the dual diagram to this diagram, let's just draw this the dual picture here, where I have this picture. This would be the centers of the punctures, and then I will draw this diagram here, okay? Which I can also represent here. It's like I have some lines here, and then they connect out at infinity. They connect there at infinity, okay? And now notice that what we have here in this graph is exactly the graph that we have here in the gauge theory. In the gauge theory, if I collapse these lines, if I think that this lines is just a bundle of propagators, I can collapse it and draw a graph, which is just in this case a triangle. Okay? Where now it's a graph where each of this guy comes with an integer L, which tells me how many propagators there are. For example, if this is operator 1, 2, I would say that L1, 2 equal to 1. And if this is 2 and 3, I would say here that L2, 3 equals to 2. This is what's called a metric graph. It's a graph that also has length associated to the edges. So it's a ribbon metric graph. And this would have L1, 3 equal to 2. Okay? And this graph here is a graph would be identified with this green graph here. Okay? So we see that these points here, these red points here that are appearing here, they are like our hexagons. I can think of this point as like my center of my hexagon. If I were to draw it in this picture here, I would put a cross inside the triangle and a cross outside the triangle. Okay, so this would be the inside of this hexagon, and the outside, they would be exactly this cross and this cross, which are the inside of this green triangle and the outside of the green triangle. Okay? Now, this can actually be made a little bit more precise and people that do string theory, they can make these pictures more precise using what's called the Streble differential, which is a way of putting coordinates in a nice way in a string theory diagram. So these lines, the statement is the following, is that there exists a nice differential phi, which is a quadratic differential, such that phi, this quadratic differential, has double poles at the punctures where you insert the operator. Okay? So phi, close to each puncture, phi behaves as z minus, well, depends the 3 points, say xj square, there is a double pole, with a residue that you can fix. Okay? The residue is your choice. So let's choose with some insight, and I will explain soon why, let's choose the length to put of the residue to be the size of the operator. For example, this has 3 propagators, so we say this has length 3. This has 4, we say this has length 4. And the other one has 3 as well. So let's say that the residue, but for now we are not making a connection yet. We are saying that given, the statement is given some Riemann surface, there exists such differential which has double poles at the punctures like this. Now, then it obeys another property, but for now let's focus on this one. Then if I zoom in close to each puncture, you see that there are lines where square root of phi dz is real and lines where it is purely imaginary. Okay? So for example, if I have just 2 punctures, this differential would be just 1 over z square, and the lines where it's purely real and purely imaginary are just the sigma lines and the tau lines. So these lines here, which go around the operator, these lines here, would be the lines where square root of phi dz is purely imaginary. So if I divide by I, it will become a real number. And these other lines, which leave the operator, they are called the vertical coordinates. These are the lines where square root of phi dz is real. Okay? So close to each puncture, this differential, just by computing where its lines are imaginary, they start putting some coordinates on my worldsheet. Okay? But then the statement, and this is the theorem of Streble, is that given a Riemann surface with some n punctures and genus G, okay, the theorem is that there exists a unique differential where the surface is nicely divided into these disk-like regions with these critical lines that separate these disk-like regions, and that cover the full surface. Okay? Is it clear? Therefore, because of this, you see that there is a map that given some point in the moduli space of Riemann surface, so I have the moduli space of Riemann surfaces, of n punctures and genus G, and there is this differential that allows me to coordinatize my string, and then define these graphs for each point on the moduli of the moduli of Riemann surfaces. So there are the space, the moduli, this would be the moduli of Riemann surfaces. And now here, let's write an equation. This would be the set of metric graphs of this genus and this number of punctures. And we see that given a Riemann surface, through the construction of this differential, I obtain a precise Riemann graph. But in fact, the map is not one-to-one, because given a Riemann surface, I had the freedom to assign a length to each operator. So the map is actually, there is an extra factor, R. I choose a positive integer number for each residue. And then the theorem is that these two spaces are isomorphic. That parametrizing the space of Riemann surfaces, I can think of as giving basically the space of Riemann graphs with an integer or with a constant at each vertex. Okay?
So for the pair of pants you drew, that's just genus 0.
The pair of pants that I drew is, let's now just see, because it should be kind of trivial for the pair of pants. So now let's understand that. Let's now revisit this statement for the pair of pants, where the moduli should be trivial, and then for the sphere with 4 punctures, where it should be slightly interesting.
So it's more complicated. You need at least one function for this theorem.
Yeah, probably, but okay, we don't care about one-point functions in n equals 4, yes. Okay, that's true. Good. As I said, everything I'm going to say here is kind of motivational and cartoons. And it serves as inspiration to motivate a proposal that is conjectured for the precise way of computing in n equals 4 super Young Mills. So I don't think there is a point in being extremely rigorous, because at some point there will be some huge jump in some guesswork. So I think it will be overkill. But it's indeed true that this requires at least some reasonable number of punctures such that we can start drawing indeed this hexagonalization of the Riemann surfaces. So what was I saying? Good. So now let's think a little bit more about the particular case that we were just doing, which was genus 0, as you were pointing out, and 3 punctures. So if you have n equals 3 and genus 0, let's see what happens first in the gauge theory. So in the gauge theory, you see that you have 4 propagators, and some propagators go here, right? We said 2 go here, 2 go here, and 1 propagator connects these 2 operators. Notice that there was no freedom. As soon as I say that I have 4 fields here, 3 fields here, and 3 fields here, the number of propagators is totally fixed. That's simply because the total number of propagators in operator 1 either go to operator 2 or go to operator 3, and you have 2 other similar equations, so you fix all the lengths, giving the lengths of the operators. Right? So you just know that propagators are conserved. So here, it's exactly the same thing. So here we have this differential, and the residue here is fixed to be these 3 integers, 1, 2, and 3. So the integral around that differential is fixed. But the integral, you see, the integral now of the differential from this point to this point, say this integral here, of this differential, I can now use this differential to assign lengths to my graph, right? So given that this, I can use this here to assign a length along a path where these lines are purely imaginary. Okay? So what we do is the following. To this green graph, let me assign lengths in the following way. Let me say that this line here has the length, which is the integral of this Stribel differential along the line that crosses this line here. So you see, you have this line here that crosses this line. This is the length of this segment here of the dual graph. This segment here of the dual graph here would be given by this segment here that pierces this guy here. You see? But by contour argument, this is just the total sum of the lengths is just a closed integral that is fixed to be the residue there. So this length plus this length is nothing but the integer but the number that I put here. So the equations that I would write for this length, let me call again these operators. What was I calling them? 1, 2, and 3. If I call this L13 and this guy L12, by exactly the same contour argument, I get an equation for this length, which is exactly the same equation as in the gauge theory. Okay? It is just contour manipulation, that this length plus this length are L3. This length plus this length is L2, and this length plus this length is L1. So in total, all the lengths of this graph are fixed. So I obtain a graph, which is exactly this graph here, this triangle, this green graph. The final graph is exactly the same, where these lengths, L1, 2, are fixed exactly as before to be L1 plus L2 minus L3 over 2, and similar for the other edges. Okay? So it's okay, it's fine. So it just means that you give me a 3-punctured sphere, you choose some integers, and there's nothing more to fix. And that's fine, there's no moduli. It's like in the gauge theory. You give me some operators of given lengths, I start with contracting them, and there's no freedom in how many propagators connect to each operator. Okay? Is it clear? Okay, good. So now, let's have some fun and consider, with this experience, what we get for a 4-point function. Okay? So let's now do a 4-point function. So let's start. Yes?
In that equation, you have r plus to the n, but those were really integers?
That's right. So what we are saying is that the gauge theory, each graph in the gauge theory, it's one point inside the moduli space. There are more points, because you don't need to have integer numbers. So it's the space that naturally appears in the free gauge theory is like a bunch of discrete points in the moduli space of the Riemann surface. So it's there, you have the moduli space, and you have a bunch of points, which are when these lengths are integers. So this picture of emphasizing that there is the big moduli space of the Riemann surface, and then these points there inside where these lengths are integers, and that this could be a very important subset, was very nicely emphasized by a paper by Razamat, which is called, by Shlomo Razamat, which is called The Dual of a Free Gaussian Matrix Model, I think. It's a very nice paper. Yes?
If you study more general points, does that indicate some analyticity in R charge?
Analyticity in R charge. Ah, yes, I see, good point.
Then you need to think complex charge.
Yeah, it could, in principle, yeah, why not? Once you have analytic results, yeah. Who is afraid? We are not. Okay.
Also, sorry, is this triangle thing was only true at lambda proof coupling equal to 0 or not? Because you can have as...
That's right. That's right. So here I'm getting inspiration from very weak coupling gauge theory and from string theory-like cartoons to start seeing these hexagons appearing. Okay? So we see, so now let's go on and study a 4-point function. And instead of starting with the gauge theory, let's start with the string theory to see how the string theory would lead nicely to the kind of things. Let's do the opposite order. So let's start with the string theory and say that I have 3 strings coming from these 3 points and 1 from infinity. Okay, so let's draw the string. So it starts growing. Let's hope it works. and 1 comes from infinity. Okay, good. Okay? So you see what's happening, that now we get 1 point trapped here. Let's use red. We were using red for the hexagons. This would be the hexagons, as we will see. So these are these critical points, and the lines that connect them are the critical lines of this triple differential. So this would be 1. There is another point trapped here, another point trapped here, and another point trapped here. Right? You agree? As it's growing, you get these trapped points. So now let's connect them. So we get this, 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 and this. Okay? So the graph that we would get in this case is this. And the dual graph, if I were to draw a dual graph connecting, would be this graph here. Okay? No. I just drew the critical lines and the lines that connect it. Okay? So this would be the critical graph, the red one, and the white one, which, yeah. 1, 2, 3, 4, 5. Yeah, there is one line missing. Sorry, yeah. Thank you. Yeah, in the white one, yeah. Okay? And this would be the dual white graph. Okay? So the dual white graph, it might not be obvious. Let me massage a little bit. It's the same as this graph. If you see, if you connect the points, it's just this. But here it looks, I just shifted a bit the vertices. Okay? And now the idea is to identify this graph with a gauge theory graph, where we have 4 punctures. This would be operator 1, this would be operator 2, this would be operator 3, and this would be operator 4. Okay? And remember, these lengths here, the length that I associate to these 3 lines, okay, I read them off. Say, if that operator is operator 1, those 3 lengths are the length of this segment, and this segment that pierce that line of the dual graph. And they add up to the length, to the integer that I associate to this puncture here. Okay? So in this graph, this length, this L prime, and this L prime prime, L plus L prime plus L prime prime is the length of operator 1, and similarly for the other lengths. Okay? So clearly, this is a graph I could draw in gauge theory. I could draw this graph in the planar limit, right? Just make these lines fat. Right? So this is indeed a graph in the gauge theory. Do you agree? It's just connecting the free propagators. And there, in the gauge theory, what would I have? I would have some operators of length, say 10, 10, 10, 10, whatever. And then the lengths, they add up to the length of the operator. The propagators need to go somewhere. So it's exactly the same conservation of propagators that I would draw. But now let's see how constraining this is, these conditions are. We have 6 lines. You can count 1, 2, 3, 4, 5, 6. Or here, 1, 2, 3, 4, 5, 6. As you pointed out, I was missing 1 line. So we see that there are 6 lines. That is, there are 6 L's. And there are 4 constraints, right? Which is L1 equal to some sum of L's, and similarly for L2, L3, and L4. So there are 6 lines, 4 constraints. So after doing this, we are left with a double sum of 2 L's. We can choose L, L prime. Okay? So even if I fix this particular topology, right? Just by saying that the total number in the gauge theory, right? I would have this 2-dimensional sum. And what do I expect for the moduli of a Riemann sphere with 1 puncture? Right? This should be contrasted. What do I expect here? I fix this position of the punctures. I fix 3 positions, and I integrate over the position of the 4th puncture. And it's an integral over complex position, so it's a 2-dimensional integral. So the 2-dimensional nature of this integral is what we would match with the double sum that appears here. Now it's the double sum, it's not a double integral, and that was related to the comment before. This is picking a set of discrete points in this two-dimensional manifold. So there is a two-dimensional manifold where we integrate, and we are in the gauge theory summing over a discrete set of points inside this two-dimensional manifold. Okay? So this is how, this graph here, you see that in the gauge theory, I fix this puncture, say this, imagine I fix this one, and the one at infinity. Right? And now start moving this one. Let this one be Z4. And start moving it. What happens as you move? You deform this graph, right? You start deforming this graph. By deforming, what happens? If you don't move much, the graph is the same, but the lengths are changing, right? So the two-dimensional integration over this Z4 is, through a complicated map, a two-dimensional integration over two of these lengths you choose. Right? You agree? So there is a map between the integration over this Z4 and the integration over two of these lengths. In practice, it's tough to construct this triple differential. We know it exists, but it's not easy to trade the integration over the fourth puncture by the integration over two lengths. But it exists. It's just a bit hard to find explicitly. Okay? Now, if you move a lot, this graph would jump to another graph. You could, for example, eventually move so much that you would jump from this graph to, say, a new graph like this, for example. But that's fine. In the gauge theory, these graphs are also graphs that we should add. Okay? And the theorem was that the full set of graphs is the full set of, to really integrate over the moduli, I need all the graphs. So the claim is that this other graph in the gauge theory, I would also get it from a picture. But I would have to move this point a little bit. I don't know. Maybe if I put the point here and start drawing, I get this other graph. It's a question of playing a bit. If you play a bit with these points and start drawing, immediately we will get this graph easily. Okay? But this graph, you see it has again 6 lines, 4 constraints, so the dimension is okay. So locally, close to each graph, I have a two-dimensional sum. But the graphs jump as I move away in the moduli. So it's like the moduli space has different regions associated to various graphs. And then in each region, I move around in that region, and that would change the lengths associated to the various lines of the graph. And in the gauge theory, I don't move smoothly because I only have integers. So I move discretely in a discrete set of points inside the moduli space. And we see that here, there are one triangle here, another one here, another one here, another one here. And similarly here, there is 1, 2, 3, 4, which are nothing but the dual of the 4 points that we get here, these 4 critical points. And that's the statement that this 4-point function is obtained by gluing 4 hexagons. So let's remember why they are hexagons, because now they are looking like triangles. Remember that they are hexagons because we have 3 big lines here, and we have 3 small lines here from the operator. So these lines often we don't see. When we collapse this into a point, we often don't see these lines. So then they look like a triangle. So that's what's happening here. In these graphs, if I were to resolve this, here I would see something like this. And then I would add up a little bit of line to each of these hexagons here. Okay? So it's really, these triangles are really hexagons if I blow up each puncture into a small circle. Okay? But you can try to draw, like I did for this 3-dimensional pair of pens. You can draw what you would draw for this 4-point function. So let's draw a 4-point function like this. Okay? And if you see, this graph that I drew here would correspond to cutting the pair this like this, like this, like this. So you see here is one hexagon. Let me put a cross to indicate this would be like the center of this hexagon. And then I would cut it like this, like this. And then there would be 3. There is another one. Like this. And we have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6 lines. This should be enough. Yeah. Okay? And you can see that this is a way of decomposing this 4-point function into 4 hexagons that is coming out naturally here. Okay? So let's make a few small comments. So the first small comment that we can make is that the 3-point function itself, even though we are talking about a CFT, in this case is not a fundamental object. The 3-point function, we will think of it as gluing together 2 hexagons. Right? We are going to obtain it by gluing together, stitching together these 2 hexagons. And the second comment is that even the 4-point function, if I compute a 4-point function, of course, it's not obtained by, we obtain it by gluing together 4 hexagons, but we don't do it we don't group them first into a 3-point function. I mean, I don't want to write not equal because it's equal, of course, but glued in a way, my God, this is boring, which is different from C1, 2, 3 times C1, 2, 3. You see, this picture is not a decomposition into, I construct one 3-point function, I construct another, and I glue like I would do in a it's really, it's what it is here, right? It's this picture here, where I have this hexagon, I have this hexagon, I have this one, and I have this one. But they are not glued in first constructing 2, then constructing 2, and then gluing them together. It is a different way of cutting this. Okay? So in the afternoon, I prepared a problem where we will explore further these pictures. You will be asked to try to say, draw what this picture would be, one example of this picture for a 5-point function. And understand in general how many hexagons you expect. For example, here we got 4 hexagons. For the 3-point function, we got 2 hexagons. How many do you expect for an n-point function? And it's basically the same kind of arguments that we are more used to do when we glue things with pair of pens. When we glue things with pair of pens, it's easy to see for any genus how many pair of pens we need. And you are invited in the afternoon. There is a small problem where you are going to play a little bit with these hexagons. And the exercise is basically to say, generalize this observation here. Here we saw that the dimension of the discrete moduli space we get in the gauge theory matches with the dimension of the continuous moduli space that we get in the string theory. Now you could try for a 5-point function. For a 5-point function, I expect a 4-dimensional moduli because I integrate over 2 punctures. Do I get 4 sums for a 4-point function? And so on. And that's what the exercise is about, precisely generalizing and cleaning up a little bit what we have been doing here. So if there is any question about this part, please ask me now.
So the one integral there.
Yeah, it's 2-dimensional because it's the position of the puncture in the complex plane.
Like string amplitudes, I would have said there are 4 punctures and you subtract 3 from formal killing vectors and get that.
Exactly. So you gauge fix 3 of them, and the 4th one you have to integrate over.
Okay, so it's not a coincidence that these agree?
Well, after this theorem, they have to agree. So it's of course not a coincidence. It must work. So when you will do a 5-point function, you better find 4 sums equal to, that correspond to the 2 punctures that you would integrate. So it's a good exercise that you draw a 5-point function with propagators, you draw these skeleton graphs, you see how many constraints you have and how many lengths you have, and you must be left with 4. Because you want to get a 4-dimensional sum in the end, which is 2 plus 2. Yeah? Is it clear? Okay. More questions?
Can this decomposition be made precise for correlators network DCF?
Some things, yes. So for example, tomorrow I will show explicitly how to think of this object here. of this hexagon and do some computations in the 2D CFT of a free massive boson of computing correlation functions of these hexagon operators.
Sorry, how is the free massive boson a CFT?
No, not CFT, sorry, a quantum field theory. Then you can take the massless limit if you want. But in CFTs, when you have a 2D CFT, these operators were actually introduced previously to consider entanglement entropy and other things. Okay?
Right, because it seems that you're decomposing a circle into 3 intervals, and that's kind of a wild operation, because the Hilbert space of states on that interval is complicated. So you want to decompose in that way.
That's true, yeah. Naively, it looks complicated, yeah. Yeah. So what Sheen is pointing out is that we have some Hilbert space on this circle, and now we are saying, okay. So what I'm saying here basically is, let's, instead of doing the string path integral over the full thing, let's do the path integral over this hexagon, then over this hexagon, and then let's glue them together. But of course, I mean, it looks a bit dangerous. What are we going to do with the Hilbert space on each of these segments when we are gluing? And the answer is that actually the first thing we understood when gluing this, which led to this proposal of the hexagons, came exactly from observations related to how this Hilbert space got split in n equals 4. So it turns out that in some cases the division of the Hilbert space is not so hard. If you imagine the Hilbert space being some gapped system where you have particles moving in a line. Because when particles move in a line, when you cut the line, what happens is that the particle is to the left or to the right after you cut. So there the Hilbert space is easy to describe, right? The Hilbert space of gapped particles in a line, you cut and you see where the particles end up. If it's gapless, it looks more tricky, right? Then they're more delocalized and so on. So one would have to start putting it gapped, cutting, taking the gap to 0 limit and study what happens. So that's one option. The second thing we can say is that often we are inserting here a vacuum operator. By a vacuum, it means a BPS operator, which has no inner structure. And then when you cut, the claim is that you get vacuum on each of the segments as well after you cut. So if you imagine, sometimes if you imagine you are inserting the vacuum, again in a gap theory, when you cut, you would get the vacuum in each segment.
Sorry, that's, for a massive boson even, that's not true, right? Like, it has a Compton wavelength, it could be smeared across the cut. Like, that's why we
If
have
it's free,
entanglement in the CFT, then, or QFT. It's not on the left or right.
depends on which basis you are considering. But yes, I agree, yeah. But let me describe, I think tomorrow that we will do some more explicit computations with splitting this Hilbert space, maybe even today. Okay, so let me continue drawing some pictures, and as I said, tomorrow we will start computing with these guys. But let me point out here what is going to be the basic idea to compute this correlation function is going to be that we decompose into these hexagons, but then we have to glue them back together, right? So even if we could do the path integral here and the path integral here, we have to glue them along this line. So what does it mean to glue along this, to glue anything along a line? I would insert my resolution of my identity along this line of all my states that I can create on this segment here of psi, psi, and I would have to do it for each line where I'm cutting. And then what would it mean? It would mean that this object would become, well, there are 6 lines, so that's a bit unfortunate. It would be a 6-fold sum for a 4-point function. Okay, so there are 6 sums here because there are 6 lines. But then what is my integrand? What am I summing? For example, here I would have an operator which is an hexagon that takes 3 slots, 3 Hilbert spaces, one here, and one here. So it would be like an hexagon operator acting on 3 states, psi1, psi2, and psi3. And if I call all this thing hexagon, then I have times another 5 hexagons like this. So this is the operator, and this is the operator acted by some state in my Hilbert space. That's what's called a form factor. It's when you take an operator and you hit with it. So this thing here would be called an hexagon. It's the expectation value of the hexagon on some physical states. So this would be an hexagon form factor. So you see that it's in this sense that this is a building block, in the sense that I have the full 4-point function. That's hard to compute. And the best we can do right now is say, well, I can decompose it. I sum. It's not just one sum over two 3-point functions. It's more sums. But then inside is just decomposed into the smaller building blocks, which are the hexagon form factors. So it's in this sense that I was saying up there that the hexagon would be the building block in the same way as the 3-point function would be the building block in a regular CFT, where we use if we were to use the 3-point functions.
Question. Shouldn't we have 4 hexagons in the sum?
Yes, you're right, yeah. I don't know, yeah. 3 more hexagons, yeah. There is 1 here and 3 more, you're right, yeah, good point. More questions?
People try splitting it in half instead of 3 first.
Could you repeat, sorry?
Did people try splitting the Hilbert space in half instead of 3s first?
So here, what Nima is pointing out is that we are splitting each segment into 1, 2, 3, right? But you see that this is in this example. In this one here, for example, right? If I were to draw this example, you see that this operator here got split into 4. 1, 2, 3, 4. But this one got split into 2, like you are proposing. 1, 2. So that's actually the second problem in today's exercise, is to draw the 3D version of this graph here. Okay, you just have to see what should you change there to get this graph here, where exactly you split into 2. And splitting into 2 was the splitting that we had here in the 3-point function. In the 3-point function, you see that each operator was split into 2. See? You have a section A and a section A prime.
And I should really be thinking the states at the end of these circles, those are in the vacuum, right? Those are some vertex operators.
They would be some, so, okay, so let's see. So here, what you put at the end of these states, they are your operators, what Shota was calling our renormalized operators, and there are many such operators here. What could these operators be? They can be these BPS operators, or they can be the rest. Right? So if they are BPS, they are like the vacuum. It's just ferromagnetic vacuum, like before all spins up. And the idea is that those, we think that they have no structure, they have no excitations there. They are just empty spin chain in the vacuum. And these guys, these non-BPS states, we think of them that you have my closed string and there are some excitations here. For example, this would be 4 magnons in the language that Shota was describing. Okay? So here is a computation anyone could do now at weak coupling. You can take the wave function, so here's an exercise one can do. We could compute this 3-point function, where here we consert the wave function of this beta and zats. Okay? You remember that this was a sum over n factorial terms, where n is the number of magnons. Just all the ways that magnons can scatter, right? So there is an identity, there is a term where they scatter, blah, 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 blah. Right? And now you start weak contracting them. For example, the magnon is here, and you weak contract with a magnon here. Or a vacuum is here that you weak contract with a vacuum here. Or maybe the magnon is now here, and you weak contract with a magnon here. And you start doing this combinatorical problem. It's just combinatorics. You just take this wave function, which is a linear combination of operators, and draw this. Okay? And actually you can do it, just to simplify our life, you could say that this guy is a non-trivial state with n magnons. And these two guys, you could even make them be ferromagnetic vacua, which are BPS operators. Okay? And there's still some combinatorics, interesting, because you have n factorial terms, and you have to distribute the various ways where they go to each operator. And what did we get when we did this computation a few years ago? We got that the result of this combinatorics, it's actually an interesting problem in doing the combinatorics of where they go, was given by a sum over all ways of separating my magnons, which have momenta P1 up to Pn, into two groups. And the result was something like some function of one group times a function of the other group. Okay? And this, if you want, was the first evidence that came for us that the three-point function was not a fundamental object, but that there was something more fundamental that was separating into two groups. So it so turns out that in this case, you can literally think that I have my magnons moving around, and when they are moving around, at some point, I cut my pair of pants into two and say 3 magnons got trapped here and 1 got trapped there. And I have to sum over all possibilities, who got stuck in the front and who got stuck in the back. That's an interpretation of this combinatorical problem. The combinatorical problem is, this is correct. It's just the result of the computation. And then there was this interpretation. It can be that I'm cutting into two and I'm either in the front or in the back. So this interpretation, if it's correct, it also provides data, because it says, well, but then this guy I can interpret as exactly these hexagon form factors. And then I start learning about these hexagon form factors, that once I start learning about them, I can put them in more complicated objects and see if things are working out or not. Okay? So now the precise way on how we cut these states, as I said, the precise way of cutting it into two, I agree that naively it could be a subtle business, but here it seems to be just that the magnons are either on one side or on the other side, at least when the operators are large. Okay? At what time should I finish? No one knows?
I think we started like 15 minutes late. And you were scheduled to end at 1:30, so...
So I have 20 minutes.
But if people start looking really hungry, they might get angry.
I see. Okay. Okay, so then let me just make a few more comments about let me make a few more comments, a few more general comments about integrability and about the path we are taking. And then I will do a very quick computation that partially I already hid before behind one of the blackboards, so we can do it in 5 minutes. Okay. So let's see. So I just want to point out that normally in integrability, we proceed in the route that Shota is describing. It's first you study one particle and you learn what's the energy of one particle. Then you study two particles and you learn what's the S matrix of two particles. Then you take these two objects and you obtain things like the spectrum, for example, in some finite volume. Okay? Because you know how to put particles in finite volume. They just move around and they scatter with the other guys, and you can quantize their momenta and obtain their spectrum. Okay? And then, normally, from here, people go on to studying more interesting things, say, from the point of view of condensed matter, when they study some one-dimensional materials, which would be, for example, correlation functions. Where you take, say, the magnetization here, the magnetization there, and you study, say, the two-point function. How does it decay on the spin chain, and so on. Okay? So we do correlation functions of local operators. Okay? And here, however, the way people construct this step here, perhaps is not exactly what we should expect to be the path that we should follow in this business of using integrability for solving a gauge theory or a string theory. And the point is very basic. It is just that a string theory which is a theory of this vibrating worldsheet, is not a natural theory to have local operators. It's not natural to ask what is the expectation value of some displacement of the string here or here when the worldsheet is vibrating and there's no notion of the points on the worldsheet, right? So on the worldsheet, what is natural is the S matrix. This S matrix is very good. I just start at minus infinity, I send something, it happens here, and I get it in the future. That's good. But asking inside what's the correlation function between some field here and some field here, it doesn't seem to be a natural question to ask in a theory where the space-time is fluctuating, like the worldsheet, right? On the other hand, there are these operators, which turn out to be exactly these, which are called branch point twist field operators. Okay, which are almost the most straightforward generalization of the S matrix, in that what these operators do, what we do when we consider this operator is say, I still want to send things from infinity into the past, say 2 particles from the past into the future, but I want to change my causal structure such that, for example, there is, instead of having just here, there is left, and there is right, and there is past, and there is future, I'll change the structure such that instead of a rotation by 2 pi, there is a rotation, say, by 6 pi. Okay? And that is what people do with these operators that insert a conical excess around some given point. I would think pictorially like this, where this operator here is hiding some Riemann sheet. For example, in this case, it would be hiding half Riemann sheet. Typically, people use it with integer number of Riemann sheets. But here, just the complex plane has future, past, left, right. And now I want to include 2 more sectors, say another left and right. So I need another half of Riemann surface that I hide under there. Okay? And these operators that create this monodromy around, normally they are introduced this phi n, and here n is the number of sheets that they create. Normally people take n to be integer and they use it to put the theory on multiple covers of the complex plane, say on a Riemann surface with n sheets. Because then they use these methods of replica trick to use these operators to compute entanglement entropy and other objects like this. Okay? Have you all seen these kind of things where you have a cut and you have many copies of the theory and then you go glue, 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 and that's like multiplying several density matrices to compute some entropy, some Rayleigh entropy or something from which you would compute an entanglement entropy. Okay? So these operators here, these phi's, they have this effect. They insert some conical excess such that as I go around, now instead of having just a past and a future, I have a past, a left, a right, a future, another future, another future. So I have a bunch of futures, and the causal structure is such that I would have to go around more times to come back to myself. But apart from this, changing this overall structure here at infinity, you see that I'm not putting stuff inside. I'm not saying that I have some local operators inside and so on. So from that point of view, it's also very natural to introduce these objects. They are, roughly speaking, just changing the asymptotic structure at infinity, and they are not inserting, they are not touching space-time, which is a fluctuating object there.
You really mean like Lorentzian infinity?
Yeah, I typically mean Lorentzian infinity, in the sense that, for example, here, I have this particle scattering, and often we also put a particle scattering here, for example. This would be what you would do if you would have, say, a finite world, and there would be some particle going around. This would be like computing the Casimir energy. And this object, for example, that I would draw in this picture, I would call it an S matrix, where 3 particles go to 3 particles. But these particles, here in this picture, I would call these particles here, I would call them incoming, incoming. These guys, I would call them outgoing, outgoing. And this particle that goes around, that would be the particle that interacts with the physical particles, I would call it mirror particle. And that particle is just a weak rotation of this one. If the theory is Lorentz invariant, it's the same type of particle that is just flowing here. Okay? So we have this incoming and outgoing. This I call physical. These particles, I would call them physical particles. And these ones that come from this side or this side, we would call them mirrored particles. And now, in general, I could produce particles in any of these asymptotic regions and consider this expectation value. Okay? And that's exactly what this hexagon is. When we start inserting a resolution of the identity, what it means is inserting a Fock state. So it's inserting like two operators here, two particles here, three magnons here, one magnon here, and then it's like considering an analog of an S matrix where these three magnons go two here and one here. Magnon number doesn't need to be conserved here. It could be 3 here. These 3 can go and create more and split here.
Doesn't this picture distinguish 3 sides of the hexagon from the other 3?
It does.
So how do you account for that in your picture?
This picture here, what Abhijit is saying is that this line, and this line are different from this line, right? This line and this line of this hexagon, right?
Yeah.
That's fine. So in this picture here, what I'm describing is gluing along the green lines. And this here, I'm not discussing what to do in the white lines. But you are right that we see in these pictures that there are indeed 2 different types of lines for each hexagon. Each hexagon has 3 lines that always end on physical operators and 3 lines that always cut the surface. So we can say that the lines that cut the surface, you see, they are always perpendicular to the lines where you insert. So the ones where you insert, they are what we call the physical lines. That's if the operator has excitations, the excitations come from here. If you put BPS operators, they have no excitations, you will just put the vacuum. And these lines, they are perpendicular, they are the weak rotation version of this, so these lines are what we call mirror lines. If the worldsheet theory were relativistic, the 2 theories living on the 2 lines would be the same. Because the theory is not relativistic, this theory here, the theory that we get on the mirror line and on the physical line is a different theory, but you can still obtain one from the other by weak rotation. So this hexagon object, strictly speaking, it has 6 slots. It takes 3 physical operators and 3 mirror operators. And here I'm ignoring the physical operators. In the other picture, it was the opposite. I was focusing on what comes in here, the physical magnons that come here. And I was focusing on splitting them, and I was emphasizing that one group is here and one group is here. And in this picture, I'm ignoring the details of the gluing along the mirror lines.
Sorry, but why does the mirror Hilbert space exist?
Why does the mirror Hilbert space exist? So one thing you can do is you can just, you are right that some theories don't have a well-defined mirror Hilbert space. Say if you have a non-relativistic particle, there is no sense in which you do weak rotations. If you have a relativistic particle, you look and you see I can weak rotate and change P to Y energy, energy to IP, and that analytic continuation changes, makes sense. Here as well, the dispersion relation is such that it's of square root type and it admits a mirror rotation into, it admits an analytic continuation that flips P into I mirror energy and energy into I mirror momentum. So this exists, and therefore this defines what you would call the weak rotation of the physical theory, which would be the mirror theory. Okay? Is this clear to everyone? So what I was saying is that, for example, if you have energy equal m or equal p square, right? I cannot just say energy goes, if I try to do a weak rotation, I get I p tilde equal to minus energy tilde square, and this doesn't work. I cannot just weak rotate and get energy. I cannot replace p by I energy, energy by IP, and get something sensible. Now I got something totally complex that doesn't make any sense. So that's fine. A non-relativistic particle, I cannot weak rotate, and that's fine. The one in n equals 4, the dispersion relation is such that this is fine. You can define indeed a mirror theory, and it works.
Are there other examples where it's not relativistic, but you can define the mirror? Like, is this phenomenon like a very common thing?
I think there are some continuum limits of some antiferromagnetic spin chains where the dispersion relation is such that I think the field theory limit would also have this kind of rotation. But no, otherwise, other than n equals 4 and ABJM, I don't know other examples. Okay, so, yeah, what was I saying? Yeah. Okay, so I will not do the computation I said I was going to do, but let me just mention something, which is okay. So, okay. Let me just make a comment about integrability. If I am to consider the spectrum, so Schotte, for example, was describing a local Hamiltonian that you have the spin chain and the Hamiltonian interacts locally on the spin chain, and there is some local interaction happening here on the spin chain. And this was local because of planarity, because you have these propagators, and the propagators need to interact between neighbors, and therefore you cannot get things that are non-local on this worldsheet. Similarly, if I consider the worldsheet theory, it's a local theory, so interactions also happen locally on the worldsheet. Right? Is it clear? Now, naively, if you start considering non-planar corrections, what does it mean to have a non-planar correction? It means that, say, a bunch of propagators pass, say, below some other propagators. So, for example, like this. Okay, and then the other ones continue normally. But these guys decided to jump from this part to this part. And what's the worldsheet picture of this? This would be, I have my cylinder, and I'm considering my time evolution, and then here there is a wormhole that connects a part of the worldsheet with some other part far away. Okay? So which is like a non-local Hamiltonian interaction here. Okay? So here we have some Hamiltonian that now starts interacting some spins J with some spins K very far away. So it starts to be a non-local Hamiltonian. Okay? So from this point of view, it was thought that n equals 4, as soon as you go non-planar, it cannot be integrable, because we leave this world of nice local Hamiltonians and we start getting these long-range interactions, and typically these crazy long-range interactions break integrability. Also, from a worldsheet point of view, I have a continuum field theory here, and I have some nice wave packets that are scattering with each other, and now one wave packet decides to go inside the wormhole and disappear. I mean, Young-Baxter, it's hard to satisfy when things start to go inside wormholes. So it looks like there's no chance this effective theory will be integrable. But that's, of course, because we are insisting of thinking that I have some system that just evolves in time. The way I'm saying that we should think is forget about this particular direction as being time, and we should think that we are cutting everything inside into hexagons. And in the hexagon, the excitations move in a perfectly factorized way. When they scatter, they obey Young-Baxter, and everything is integral inside the hexagon. And you are just using the hexagons to tessellate this surface. I'm not going to try to draw the hexagon here, but there is an hexagonalization that just breaks this into hexagons. And each hexagon is perfectly integrable. But the questions you should ask are not directly what's the time evolution, but rather what's the expectation value of this topology, from which later you can learn about the time evolution. Okay? But from that point of view, there's no reason to expect that non-planar n equals 4 is not going to be integrable and so on and so forth, like people were thinking before. Okay? It is just the same topology glued in some different ways.
Sorry, why is the non-locality? I thought even if you went to finite lambda, you had some non-locality in the Hamiltonian.
It's not non-local. It's just a slightly larger interaction. It's like having more derivatives in the Lagrangian, but it's not f of x times f of y separated. You are just increasing a little bit the length. Okay? Okay, I think I'll stop a bit earlier, even though I would have some time. But I think this is probably a good point to stop. So next time, I will start by recalling how we use these very similar operators for computing entanglement entropy of some simple CFTs. I will then, in that language of CFT, compute what should be the anomalous dimension of these operators that insert conical excess. And then we will go to the free massive particle. Now it's not a CFT, it's a gapped system. There the language will be very similar to this. We'll have a Hilbert space, we have a gapped system, and we'll start studying correlation functions of these objects, and then we'll study the UV limit and match with the anomalous dimension to get some further intuition. So tomorrow we'll be computing heavily with these operators to put some flash on these cartoons. Okay, thank you.